Hello, everyone. I'm going to quickly do these limits. So the first limit here, as x approaches -2, we can just plug in -2 because it exists, and we get -8. This is -40 minus 12 plus 8 minus 2 minus 52 minus 54 plus 8 is minus 46, I believe. 2, 4, 8. I think that's right. But the point is just plug in -2. For this one, you just plug in 3. So if we plug in 3, that will be 9 plus 9 minus 2. That's square root of 16, which is 4. All right. Next problem, problem number 3. Here, we're approaching -3. So we have to take the limit as x approaches -3 of x plus 3 times x minus 2 over x plus 3. Cancel to fill in the hole. As x approaches -3, plug -3 into the remaining, and you get -5. Here, as h approaches 0, we wind up with 0 over 0, so we can multiply out the top. If we multiply out the top, we get 25 plus 10h plus h squared minus 25 all over h. The 25s cancel, and then every term on top has an h, so all of the h's will cancel. And we are left with 10 plus h, which gives us 10 as h goes to 0. Because once we cancel, we can plug in, problem's gone. Here we have to multiply by the conjugate. So it's 16 plus h plus 4, rad 16 plus h plus 4. The numerator winds up being 16 plus h minus 16, which is just 16 plus h minus 16 over h times square root of 16 plus h plus 4. The 16 and minus 16 cancel, and then the h's will cancel. So the numerator will be 1, and then when we plug 0 in, we get rad 16, which is 4, plus 4 is 8. Here we have to factor. So the numerator is a difference of 2 cubes, or you recognize that 3 is a root, so we can do synthetic division with 3. Either way, we get the numerator factors into x minus 3, x squared plus 3x plus 9. And the denominator factors into x minus 3, x plus 3. The x minus 3's cancel. The new denominator is 6. The new numerator is 9, 18, 27. 27 over 6, or if we divide by 3, 9 over 2. Problem number 7. 1, 2, 3, 4, 5, 6. Yep. Problem number 7. Sorry about that. Problem number 7. Once again, we plug in 7 and we get 0 over 0. So we have to again multiply by the conjugate, similar to what we did in the other problem, x plus 18 plus 5. Note again that we will not multiply out the bottom. Limit as x approaches 7. X plus 18 minus 25 over x minus 7 times rad x plus 18 plus 5. The numerator, when simplified, becomes x minus 7, and that's convenient because the x minus 7 will cancel with the x minus 7. That leaves the numerator as 1. And then when we evaluate the denominator, we get rad 25, which is 5, plus 5 is 10. Here, 2 ways to simplify this. I'm going to do the more efficient way. You could multiply this by x over x, this by 3 over 3, get a single fraction in the numerator, and then multiply by 1 over 3 minus x because keep, change, flip. Instead, I'm going to multiply the entire numerator by 3x and the entire denominator by 3x. This becomes the limit as x approaches 3. And I do this again because when I plug in 3, I get 0 over 0. This first term, 1/3 times 3x, becomes just x. The second term, 1 over x times 3x becomes 3. The denominator becomes 3 minus x times 3x. And these cancel to give you -1. So then as x approaches 3, this term in the denominator is 9, which gives you -1/9. Number 9 is an interesting problem. As t approaches 1, this limit from the right will go to infinity. From the left will go to -infinity, so it won't exist. This limit also will not exist. And yet, if I have 2 limits that don't exist, that doesn't mean that their difference doesn't exist. The only time I can take the limit of a difference, break this up, so to speak, and take the limit of this minus the limit of that, is if the limits actually exist. Since the limits here don't exist, I have to do something to this term inside the parentheses. So what I'll do is I will multiply this guy here by t over t. And when we do that, we now have common denominators, so we can subtract. And when we subtract t minus 1 over t squared minus t, that's the limit as t approaches 1 of t minus 1 over t times t minus 1. Cancellation. As t approaches 1, t approaches 1, I get 1 over 1, which is 1. Again, the limit of a difference right here is only the difference of the limits, limit of this minus limit of that, if these limits exist. And since at least one of them doesn't, you cannot just break up the limit like that. Okay, this is the greatest integer function. So just a little reminder, the greatest integer function is a piecewise function. We're approaching 3. So since we're approaching 3, we should look at what's happening near 3. So if I approach 3 from the left, from the right, I get 3. If I approach 3 from the left, this function is 2. And I don't really care what's happening anywhere else. This is the limit as x approaches 3 from the right. That's just 3 because I'm approaching from the right. Here, as x approaches 0, this is again a piecewise, so I'll look at left and right. Remember that absolute x is equal to this. So we start by approaching x from the right of absolute x over x. That's equal to the limit as x approaches 0 from the right of, if I approach from the right, absolute x is just x. And x over x is always equal to 1, except at 0. But since I'm approaching 0, I don't care what's happening at 0. So the right-hand limit is 1. Similar analysis, if I approach from the left, I wind up with the numerator being negative x over x. That winds up being equal to negative 1 everywhere except 0, but I don't care what's happening at 0. So the limit of that constant is negative 1. Since the left and right-hand limits are not the same, this limit does not exist. Number 12, same exact idea, except I would use x plus 3. And when I do this, what's going to wind up happening, I'll do this kind of quick so you can follow along. If I do negative 3 from the right, the numerator will be 3 times x plus 3. The denominator winds up being right x plus 3. This limit winds up being 3. If I approach from the left, this will wind up being 3 times x plus 3 over negative x minus 3. This winds up being negative 3. So once again, this limit does not exist. That was number 12, yeah? Okay, number 12, good. Okay, 13 through 18. So if I approach 1 from the right, if I'm approaching 1 from the right, then I'm bigger than 1, so that's this one. So I'm approaching 1 from the right, I use this function. As I approach 1 from the right, that's the limit as x approaches 1 from the right of x minus 1, and that's just 0. Okay. If I approach 1 from the left, 1 from the left is right here, so it's this function. So if I approach 1 from the left of 3x plus 3, I get 6. So this limit does not exist because the left-hand limit is 6 and the right-hand limit is 0. And now I can do the same exact analysis for negative 1. I'll just give the answers. If I approach negative 1 from the right, I'm using the middle function, so that's 0. If I approach negative 1 from the left, I'm using the top function, that's 0. Since the left and right-hand limits are the same, the limit in general is 0. Okay, so as x approaches 9, there's no problem here. I can just plug in. So if I just plug in, square root of 9 is 3, and square root of 16 is 4, so that's 5 halves. No trickery there, you just plug in. You should always check. Here, I'm approaching negative 5 from the right. That makes the numerator negative 3 and the denominator go to 0. So that's a problem. So remember what we have to do here is we have to do some analysis. So The numerator is going to negative 3. How is the denominator going to 0? Well, the denominator will always be x plus 5, if I'm approaching from the right, will always be greater than 0 when x approaches negative 5 from the right. So the numerator goes negative. The numerator is negative. The denominator is positive. Negative divided by positive is negative. This shoots off to negative infinity. Number 21, we did something similar in class. Remember that we need these two values because when I plug in 4, the numerator is 0. This becomes 1. This becomes 1. The whole thing goes to 0 over 0. So x minus 5 is equal to x minus 5 or negative x plus 5, depending upon where x is. And x minus 3 is equal to either x minus 3 or negative x plus 3, depending where x is. And since I'm approaching 4, I will be less than 5. And since I'm approaching 4, I will be greater than or equal to 3. So I can substitute in for the absolute values with these pieces because I only care what's happening infinitely close to 4, and that only concerns when I'm less than 5 and when I'm greater than 3. So this is the limit as x approaches 4 of x minus 4 over negative x plus 5 minus x minus 3. That's the limit as x approaches 4 of x minus 4 over negative 2x plus 8. And then I can factor the numerator. That's the limit, denominator of x minus 4 over negative 2 x minus 4. Cancel. And I once again, like the previous problem, get negative 1/2. Okay, 22, 23, and 24, I'm doing this function. As x approaches 2 from the left, I'm dealing with this guy. So I get 0, because if I plug in there, it's nice and polynomial, I get 0. If I'm approaching from the right, I'm dealing with the x minus 1. That gives me 1. So this limit does not exist. The sign function, or as is sometimes called the sign function, lets you know if a number is positive, negative, or 0. So if I approach 0 from the right, I'm on this bottom function here. So if I approach from the right, this is the limit as x approaches 0 of 1. So I can just plug that in for sign x, which is 1. You can probably see if I approach from the left, I get negative 1. So in general, if I approach 0 from both directions, this does not exist. However, if I approach the absolute value, well, now we've got a little bit of work to do. See, we have to figure out what SGN of x is. And, well, we know how to deal with absolute SGN because it will either be SGN or negative SGN if SGN x is greater than or equal to 0 or if SGN x is less than 0. That's just the definition of absolute value. So now the question is, when is SGN of x greater than or equal to 0? And according to the definition, sign of x is greater than or equal to 0 when x is greater than or equal to 0. So this is the same thing here as saying x is greater than or equal to 0. And when is sign x less than 0? Sign x, the only time that sign x is negative, less than 0, is when x is less than 0. So I can, x is less than 0. And now I can figure out what this is using my left and right hand limits. So the limit as x approaches 0 from the right of absolute sign x would be equal to the limit as x approaches 0 to the right of, well, x is greater than or equal to 0, so this is just sign x. So this is the same answer as we got for part A, which is 1. Then I look at the limit as x approaches 0 from the left of absolute sign x. That's equal to the limit as x approaches 0 to the left of. Well, absolute sign x is coming from the left, so x is negative. So this would be negative sign x, negative sign x. And negative sign x can be written as the limit as x approaches 0 from the left of negative 1 times the limit as x approaches 0 from the left of sign x. As I approach x from the left of sign x, Right here, I have -1, but this first limit is also -1, so the whole thing is 1. So the left and right-hand limits are equal, so this limit actually equals +1. All right, number 26, find the following limits. Again, it might help to remember what this is. This is equal to 0 if I'm between 0 and 1, not including 1. This is -1 if I'm between -1 and 0, not including 0. This is 1 if I'm between 1 and 2. Okay, and then dot, 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 and dot, dot, dot. So as I approach 0 from the right, I'm looking here at the middle term, because x is greater than or equal to 0. So that's just 0. If I approach 0 from the left, I'm looking at the top function. So that would be -1. So in general, this limit does not exist. If x approaches a non-integer, so let's say x was 0.5. So, sorry, a is 0.5. So maybe it would help to write this out a little bit more. So let's bring this down a little bit, please. All right, here we go. So for this problem, we'll bring this down a little bit more. Shrink it, okay. Group, yeah, whatever, already grouped, great, okay. Do. And then we'll also remember, now I can also include 2. I can also include 2, 2 less than x less than 3, -2, -2 less than x less than 1. I don't know what that mark is there, but that's not an equal to, that's just a stray mark. So if I approach something that's not an integer, so let's look. If I'm at 0.5, well, this is going to shoot down to 0. In fact, if I'm at 0 point anything, it shoots down to 0. If I'm approaching 1 point anything, this thing shoots down to 1. If I'm at 2 point anything, this thing shoots down to 2. If I'm at -2 point anything, this shoots down to -3. So this is the same thing as just plugging in the a. See, if I'm not an integer, there's no problem. This piecewise function doesn't break anywhere except at integers. So if I'm at 1.7 or 1.8, this is always going to go down to 1. Now, what happens when I approach an integer from the right? So if I approach 1 from the right, I get 1. If I approach 0 from the right, I get 0. If I approach -1 from the right, I get -1. If I approach -2 from the right, I get -2. If I approach 2 from the right, I get 2. So if I approach a from the right, I get a. But when we approach from the left, something a little more interesting happens. So if I approach 3 from the left, I get 2. If I approach 2 from the left, I get 1. If I approach 1 from the left, I get 0. If I approach 0 from the left, I get -1. So if I approach a from the left, I get a minus 1, which is kind of cool. And then, all right, limit as x approaches 5. So if I just plug in 5, I get 0. Can I do that? Well, 1 over absolute x, I can just plug in the 5. That limit exists. 1 over x, that limit exists. So the limit of a difference, if they exist, is the difference of the limits. This is 1/5. This is 1/5. So 0. Easy. As x approaches 0, however, there's a problem. This first limit doesn't exist, and the second limit doesn't exist. So we have to be a little careful here. So once again, we'll use the definition of absolute value. X, -x, x is greater than or equal to 0, x is less than 0. And if we do that, we find that this is equal to the limit as x approaches 0 from the right of 1 over x minus 1 over, since I'm coming from the right, absolute value of x is x. I can now simplify this. This is the limit as x approaches 0 from the right of 0. And that's just 0. And notice we don't care what's happening at 0. If you take any number that's really close to 0 and you plug it in here, you will get 0. From the left is a different story, however. I'm going to use the same definition right here. So this would be the same as the limit as x approaches 0 from the left of 1 over x minus 1 over negative x. Simplifying this, I get the limit as x approaches 0 from the left of, well, that's 1 over x plus 1 over x. That's 2 over x. And now as x approaches 0 from the left, the numerator is positive. The denominator is negative and heading towards 0. Negative infinity. So this is another weird function where if you graph it from the right, this thing is just a nice flat line, but from the left, this thing shoots down, way down. All right, number 28. I think we're almost done. Yeah, this is the last problem. Okay, number 28. Find these. So the limit as x approaches 0 from the right of this. So remember that the only relevant thing here, this is 0. When 0 is less than x is less than 1, I'm coming from the right. This, the only relevant thing here is x, when x is greater than or equal to 0. So I only wrote the pieces that I need, but obviously these are piecewise functions. They have more. So the limit as x approaches 0 from the right of this thing. Oh, I don't even need absolute value yet. I don't even need this. I don't know why I did it. Don't need it. So this would be equal to the limit as x approaches 0 from the right. Well, from the right, this thing is just equal to 0 over x. And 0 over x, if I simplify that, goes to 0. And the limit of 0 is 0. Note I did not evaluate the limit from this step to this step. Here we're saying this is 0 divided by some positive number. Well, that's 0. And now that I have simplified, now I can evaluate. If I approach from the left, okay, so now I have to look at what's happening on the left. So if I approach from the left, this is going to be equal to the limit as x approaches 0 from the left of negative 1 over x. The numerator is a non-zero number. The denominator is getting closer and closer to 0. So this is either going to blow up or blow down. The numerator is negative. The denominator is negative because I'm approaching from the left. Negative divided by negative is infinity. Now notice here, I actually have absolute value. So here I've got to be very careful. And obviously it's the last problem, so of course it's going to be the hardest. So we have to take the limit as x approaches 0 from the left and as x approaches 0 from the right. And to do that, I need to figure out what the heck is going on with this function up here. So what the heck is this function? So let's see. If we plug in anything between 0 and 1, this is just going to be the regular old function. It's going to be 0. If I plug in anything between 1 and 2, this is again going to be 1. If I plug in anything between, if I plug in anything between 0 and negative 1, though, well, what happens? Well, if I plug in, let's say, negative a half, it becomes positive a half, and then this goes down to 0. Similarly, if I go from negative 2 to negative 1, if I plug in negative 1.5, negative 1.5 becomes positive 1.5, and that would go down to 1. So really, this function can never output a negative number. So if I look at this, if I look at the limit as x approaches 0 from the right of the top guy, I get that it's 0. If I look at the limit as x approaches 0 from the left of the top guy, I get that it's 0. So in either case, the left and right-hand limits will both wind up yielding me an expression 0 over x, 0 over x. Both of those go to 0, just like they did over here. So 0 over x goes to 0. So this whole limit is equal to 0. And that, ladies and gentlemen, is limits in 24 minutes. Skip to the part you need. Thank you very much, and good night. Good night.